The title of this talk is The Distribution of Vacua in Random Landscape Potentials. So in the beginning, there was the Big Bang, and shortly after the Big Bang, there was inflation. We don't actually know what caused inflation, but in string theory, there's this so-called landscape from which we can get an inflaton field that has roughly 100 dimensions. And the inflaton field is the driving force behind inflation. So in this picture of the inflation, the universe inflates when the gradient of the field is small. That is slow roll inflation. And then we eventually end up at a local minimum. If the local minimum is slightly above zero, then there is a vacuum energy term, and we can observe that as dark energy. So here is a realization on the right. Remember, this is a one-dimensional realization, and the inflaton is 100 plus dimensions. So this is really simplified. But here, in this part of the potential, the universe inflates, and then here is where we are right now. So this one has a minimum that is at zero. And since we observe dark energy, we would expect the inflaton for our universe to have a minimum slightly above zero. So some research questions. Given that we are currently at a minimum, and we have to be at a minimum, or else the laws of physics will be changing. So how likely is it to have a potential value that is greater than zero? Immediately we can say that this probability is less than 0.5, because as you keep going down the potential, as you keep going to more and more negative values of lambda, you should encounter more and more minima. That's why they are minima. They are lower than all the neighboring points. So probability with the lambda less than zero must be probability greater than the probability of lambda greater than zero. Another question is, how steep are the slopes leading into this minimum? This has implications for quintessence and also for the end of inflation. Finally, before inflation, presumably we were at a saddle with only one downhill direction. We want to know how steep the slopes are leading out of this saddle, because it tells us about the amount of inflation we have. So the problem now is that the string theory landscape is extremely complicated. And we proceed by modeling our string landscape as a random Gaussian field. The definition of a random Gaussian field is technical. Here's the definition up here. But you can think of it as analogous to that of Gaussian distributions. So here is a Gaussian. And hopefully everyone has seen this kind of curve before. If we plot, for example, the height of people or the grade students get in exams, it will look something like this. That's because even though these two things depend on a lot of different factors, as long as the factors are independent and random, and there are a lot of them, then by the central limit theorem, you will get a curve that looks like this. So having assumed that our string landscape is Gaussian random, we are assuming that even though there are a lot of interaction terms, the interaction terms are independent and uncorrelated. And this allows us to model what is otherwise a very complicated function. Hopefully everyone knows that Gaussians have two parameters. There's the parameter that controls where it is on the x-axis, and there's the parameter that controls how broad it is. So random Gaussian fields have three. So sigma 0, sigma 1, and sigma 2. They correspond to the square root of the average of the square root of the potential, the first derivative, and second derivative. And this is a complicated sentence, but we can look at the equations here at the bottom right. So if we have the field, f here is the value of the field, and you square it, and then you take the average, you get sigma 0 squared. Something similar applies for the first derivative and the second derivative. A key result here is that only this particular combination, gamma equals to sigma 1 squared over sigma 0, sigma 2, is the only one that is relevant for our purposes. That's because we can rescale the field and it will not affect the statistics. So for example, if instead of f, we had 2f, then in this realization, the field will go up, it will become bigger, but there is still only one minimum. And since we only care about how many minima there are, our statistics are unaffected, and therefore we can eliminate two of these parameters and only have one left. Gamma can be thought of as a measure of how turbulent the potential is. When the potential is more turbulent, when gamma is small, the potential is more turbulent. So turbulent here means that, for example, here the gradient is positive, and then here it is negative, and here it is positive, and here it is negative again. When the potential is turbulent, the gradient changes a lot within a small region. It can be shown that gamma must be between 0 and 1. Next, the technical details for how to calculate all these things is on our paper in archive. The title is the same as this talk. But ultimately, the integral we want to compute looks like this. So here the lambdas are the eigenvalues with the Hessian at the point. And alpha k alpha is a polynomial function of the lambdas and has some contribution from gamma and v, where v is the value of the potential. We can see here that there's a difference term, and then there is a product term and an exponential term, and then we integrate over all four of them. Having written this down, we can immediately write down what the integral is in 100 dimensions as well. But if anyone knows how to compute that efficiently, please let me know. Next, we say something about how the probability that we want varies with gamma and n. So note that as n increases or gamma increases, the probability of a minimum discrete decreases. That's because the more fields there are, the less likely it is that all the fields will reach a minimum at a point. And all the fields have to reach the minimum at that point in order to have a minimum in the inflaton. So that covers n. And similarly, when the potential is less turbulent, then we would expect fewer minima because the gradient varies less within a region. So probability of minimum decreases. However, this probability of a minimum is not what we are after. We are after this one, the probability of that lambda is greater than 0 given that we are at a minimum. So it is not a priori clear how this will vary. So, but then we can do the calculations and we get these two plots. So here, this one is for gamma 0.2, and then 0.5 and 0.8. Remember that the zone we're interested in is this one, the one where lambda is greater than 0. And we see that as gamma increases, the probability that the lambda is greater than 0 drops as well. For this curve, this blue line has n equals 3, and then the orange one has 5, and the green one has n equals 8. So again, this is the zone we're interested in. And as n increases, the probability that the minimum still has a lambda that is greater than 0 also decreases. So here are some plots in another view. As n increases, all four of the probabilities go down. And as gamma increases, it's 0.2, 0.5, 0.8, and 0.9. All four of the probabilities, the probability also goes down. And here is a counter plot of the same calculation. Gamma goes up to 0.95 here, and n goes up to 150. So we see that there is a region of parameter space where the probability drops as low as 10 to the minus 500. So string theory is said to have about 10 to the 500 minima, which is also why we sometimes say string theory predicts 10 to the 500 different universes. But there is a region of parameter space where even 10 to the 500 minima is not enough to have a single minimum with probably with lambda greater than 0. In the specific case of a Gaussian power spectrum, then you get this value for gamma. This has to be calculated. It is not obvious, but it can be done. And then for this value of gamma at n equals 100, the probability that the minimum has lambda greater than 0 is 10 to the minus 780. We can also calculate the eigenvalues of the Hessian at the point. The eigenvalues roughly correspond to the slope at the point. And in all these calculations, we're only going to look at the most likely point. So here's a plot for n equals 100 and gamma 0.9. The red line is the single most likely point. And the blue line is the most likely point with the extra constraint that lambda is equal to 0. It can be shown that the red line is independent of gamma, but the blue line will vary. So the red line looks like the Wigner semicircle with a deviation at the bottom, the small eigenvalues. If you do not know what the Wigner semicircle is, it is what the eigenvalues look like if there are absolutely no constraints. So it looks like this. And because there are no constraints, there is some probability that the eigenvalues are less than 0. However, we have assumed that we are at a minimum. Therefore, all the eigenvalues must be greater than 0. And we get this red line. We can also calculate what the biggest and smallest expected eigenvalues are. Here are four different values of gamma. And again, we have the overall peak and the peak with lambda equals 0. You can see that the biggest eigenvalue stays of order 1. But the smallest eigenvalue drops. Therefore, as n increases, the minimum becomes less and less, becomes shallower and shallower. We can also plot all the eigenvalues, like in 100 dimensions, then we have 100 eigenvalues. And this plot is for n equals 100 gamma 0.9. The orange line, remember, is the overall peak, and this one does not vary with gamma. But then the blue one is for lambda equals 0, and it will vary with gamma. We can also calculate the ratio of the two smallest eigenvalues. This will matter for quintessence. And here the orange line is the ratio at the overall peak, and the green one has a gamma 0.5 and blue gamma 0.9. And we can see that all three of them asymptote and stop increasing as n goes up. Next, we can investigate saddles. So this is the equation that we are interested in. You can see here that lambda 1 we integrate from 0 to infinity, lambda 2 from 0 to lambda 1, 0 to lambda 2, 0 to lambda 3. So this imposes the constraint that lambda 1 is greater than lambda 2, is greater than lambda 3, is greater than lambda 4, which is greater than 0. In the case of saddles, we want one downhill direction. So what we will do is that we modify these limits here. And instead of 0 to lambda 3, we change it to minus infinity to 0. That constrains lambda 4 to be less than 0. And for saddles, what we're most interested in is the slow roll inflation parameter eta. Eta is given by this factor. B prime prime is directly related to the eigenvalues. As I mentioned earlier, the slope is roughly the eigenvalue. And also V, which in the terminology of the previous slides is lambda. It's in our alpha k alpha vector factor. Therefore, we can evaluate this integral and directly calculate eta. Slow roll inflation requires that eta is much less than 1. And there is also an extra constraint, which is that the correlation length cannot be too large, or else small eta becomes trivial. So correlation length, if you've not encountered this before, it's a measure of how much the knowledge of where we are, the value of the field at where we are affects our knowledge of points further away. So for example, if you know the temperature in Auckland, then you know something about the temperature in Hamilton. Hamilton is a large town slightly south of Auckland, but you know less about the temperature at a place like Tokyo, and even further away like Venus, you know less and less. And at some point, you no longer know anything. Correlation drops to 0. A large correlation length is also unphysical in string theory, because string theory has a lot of short range terms, and if you add a lot of short range terms together, you do not expect to get a long range correlation. So the value of eta depends on what the value of gamma is, and gamma depends on what the power spectrum is. So a nice intermediate result that we get is that if we set gamma to be a constant, then we observe eta to go down with n. So this is a figure for gamma equals to 0.95 and V is equal to 0.01 Planck mass. Observationally, we must have V less than this number, 0.01 Planck mass, because we have not observed D-mode polarization. If you don't know what this is the gravitational waves due to the inflation in the cosmic microwave background. So what is nice about this is that n it goes down as n increases, and therefore even if at n equals 100, eta is not much less than 1. We can postulate that the inflaton has more than 100 dimensions, and then we will eventually get there. It will eventually work. But then when we try common power spectra like the Gaussian power spectrum, in this case, gamma is this number, square root of n of n plus 2, as we have seen earlier in the previous slide. And once again, we can plot it as at the 0.01 Planck mass, and we get this plot. So on the y-axis, we have eta over lambda to the power 4, where lambda is the correlation length. We see that this curve increases with n, which means that we will never actually get slow roll inflation unless we have lambda increasing with n. But as we have argued previously, we cannot have a correlation length that increases with n. It's not physical. Therefore, a Gaussian power spectrum does not work for inflation. You cannot get slow roll inflation with a Gaussian power spectrum. The other common power spectrum that people use is this power law power spectrum. Looks like this. In this case, we can calculate that gamma as this factor. Again, this is not obvious. It has to be calculated. And then we can take a specific value of n. So little n, that's this one. And again, we take V 0.01 Planck mass and we plot it. And then we get a number, a curve that looks like this, which is great. We see that eta decreases with n. However, when we dig deeper and we plot the correlation function, it ceases to work. So here is the correlation function. And as you can see, the further away you get, correlation always drops. However, and we define the correlation length to be the point where correlation first hits 0. So at n equals 3, the correlation length would be here. That's the point when you no longer know anything. And then n equals 4, that's here, n equals 5, and so on. It's immediately clear that as n increases, the correlation length also increases. Therefore, even though eta is decreasing with n, it is decreasing with n because our correlation length is increasing, and this is not what we want. And the power law power spectrum does not work as well. Moving on, we can try other power spectra, such as the convolution of two Gaussians. In that case, the equation we're interested in looks like this now. There's the power spectrum, and then this is the two Gaussians. So we have 4 free parameters now. That's U0, L0, U1, and L1. And the hope is that we can vary these 4 parameters such that we have gamma constant without also having increasing correlation length. So we do not want L0 and L1 to increase. We tried it and we did the calculations. The answer is probably no. It doesn't work. The details are complicated and we do not have a conclusive proof. But we believe that we cannot have constant gamma unless we allow L0 and L1 or L1 to increase. So some conclusions. The random Gaussian field approximation, it allows us to ask physical questions of the landscape and still get calculable answers, which is great because otherwise the landscape is intractable. However, under this approximation, inflation is not favored for the common power spectrum that we use. It doesn't mean that inflation is impossible, because keep in mind that all our calculations assume only the most likely saddle. And it is possible that our universe had a slightly less likely saddle. But it does mean inflation is not likely. This is especially the case because the slightly less likely saddle, the probability actually drops off quite quickly once you're away from the most likely point. It is possible that a more complicated power spectrum works. So remember that we only use 3 power spectra. That's the Gaussian, the power law power spectrum, and the convolution of 2 Gaussians. It is possible a more complicated one works. But then, if we have a more complicated power spectrum, then presumably we also have complex physics. And once we have complex physics, it defeats the purpose of the approximation. Because keep in mind that in the approximation, we cut out all the physics. We rely only on large number statistics. So by assuming complex physics, our approximation ceases to be relevant. Like, we assumed no complex physics in the first place. Yeah. So is this the end of inflation? Probably not, but it's the end of this talk. So if you have any questions, comments, and so on, feel free to let me know.